Right, okay, let's start. I think she's not joining. Real numbers, right? Okay, so it's because we have already done the chapter, so I'll just take it as a revision sort of thing. So the first topic we actually discussed in this chapter was about the types of numbers, right?
Yeah.
Okay, so let us just quickly recall. So the first type of numbers are natural numbers. Okay, what are natural numbers?
Ma'am, numbers from 1 to
Yeah, so counting numbers basically.
yeah.
Okay. So it is actually denoted by capital N. So it includes a set of like 1, 2, 3, and so on, all counting numbers. So this bracket represents a set. I mean, this complete set of number is called natural numbers. Then second, we had whole numbers. What about this, Martin?
Ma'am, this is 0, 1, 2, 3.
Exactly. So this set is represented by capital W. So we include 0, 1, 2, 3, and so on. So this set of number is whole numbers. Then the third we discussed was integers. So integers include, it is actually denoted by Z, right? So
Yeah.
this is a set where negative numbers are also included. So for example, -2, -1, then we have 0, then 1, 2, 3, and so on. So this complete set is called integers. So it has positive numbers also, it has negative numbers also, okay? So about 0, actually there is an ambiguity. Like we cannot say 0 is positive or we cannot say 0 is negative, right? Because 0 means
Yes.
nothing, right? So sometimes, in books it is written that it is a non-negative number, right?
Yeah.
You must have seen a term like non-negative. So why don't they write it positive? Why say non-negative? Why? Because if I take this set, that 1, 2, 3, 4, and so on. So I can say they are positive. Understood? They all
Yeah.
are positive. But if I have a set like 0, 1, 2, 3, 4, now because of the presence of this 0, I cannot call this complete set as positive. Understood?
Yeah, ma'am.
So I can call it non-negative. So I'm not definitely saying that it is positive. Understood?
Yeah.
So that's how we.
Yeah. Okay.
So sometimes it is written as non-negative, non-positive. So that means there's a problem about 0. That is why we write it. Okay, then next we have, now we come to fraction type of numbers and they are called as rational numbers. Okay, so they are actually numbers of this form where q is not equals to 0. Understood? Okay. Now
Yeah.
any integer is also a rational number. For example, I have -1. So is this a rational number?
Yeah, ma'am.
Why?
Because q not equal to 0.
No, but
And
it is not of the form p by q, right? It is only -1. So can I say it is rational?
yes, ma'am.
No, but why?
Because like, it gives a value.
Okay, for example, I have number 5, let's say, right?
Yeah, ma'am.
Now, can I say it is a rational number
Yeah.
by this definition? But how can you say the definition is saying that the number should be of this form, p upon q, but it is only 5. So can I call it a rational number?
Not sure.
Not sure. Yes, I can call because I can write it as 5 by 1. Okay. So now it is of the form of p by q where you can see that q is not equal to 0, isn't it?
Yeah.
So that means any integer, whether it is positive, whether it is negative, or even 0. So 0 can be written as 0 by 1, no problem, right? So it is a rational number. Understood? This one I can write -1 upon 1, no problem. So I'm not saying that p is always positive. P can be negative, right? So it is again rational. Understood?
Yes, ma'am.
Okay. So that means all integers are also rational numbers. Okay. Then obviously we have irrational numbers, right?
Yes, ma'am.
Okay. So irrational numbers, like the definition is that they are not of the form p by q, right? Understood? Where q is not equal to 0. The numbers which are not of this form, they are irrational. The examples include under root 2, right? Under root 3, under root 5, and in fact, like cube root of 2 also is an irrational number. That means whenever a number has a power of fraction, understood? Because under root 2 is what? It is 2 to the power half, isn't it?
Yes, ma'am.
Yeah, so it has a fractional power. Okay. For example, but every under root number is not irrational because, for example, I have under root 4. So if you go by this definition, so I can write 4 as 4 to the power half. So I should say
Yeah.
that it is irrational because it has power of fraction, isn't it? But no, I can write 4 as 2 square and then power half, right? So this will be
Yeah.
2 into half. So this 2 cancels out. So it will be 2 to the power 1 only, and that is 2. So this is like not irrational. Understood? So the numbers which are perfect square, if I write something under a square root, so the number which are perfect squares, for example, 4, for example, under root 16, under root 9, they will not be irrational.
Yeah.
Got it? And if I write, for example, cube root, so the numbers which will be perfect cube, for example, 8, right? Then I have 4 into 4, 16, and 3, for example, 27, cube root 27, right? It will give you 3, this will give you 2.
Yes, yes, ma'am.
So they will not be irrational. So that way I can say that 2 to the power 2 by 3, for example, will also be irrational. Understood? 2 to the power 1 by 4 is also irrational. But you don't have to deal with this kind of number. In your syllabus, you have to deal with under root 2, under root 3, root 2 kind of number only. Got it? But just to explain you. Fine, Martin? Hello, Arshia, can you hear me?
Yes, ma'am.
Oh, when did you join? I didn't see you.
A while ago.
Okay. So Arshia, today I am taking real numbers again, basically, right?
Yes, ma'am. I joined when you started it.
Okay, fine. So is this clear so far?
Yes, ma'am.
Okay, you can ask questions if you wish. So is that
Okay,
clear?
ma'am.
What are irrational numbers?
Yes, ma'am.
So basically they are not of the form of p by q, first of all, right? So in your syllabus, you will come across numbers like under root 2, under root 3, root 5 type of number. But basically, yeah, so basically whenever you have fractional power, for example, these numbers are also irrational. Okay. Now next come real numbers, right? Sixth kind of number are real numbers. Now, what are real numbers? So if you combine every kind of number, that means rational plus irrational. If you take all the numbers, so they become a set of real numbers, right? It is denoted by capital R. That means every kind of number, every fraction, positive, decimal, like whatever kind of number you have, when you take all the numbers together, they form a set of real numbers. Is that okay? Martin, I can't hear you now. Yes, Sarah, can you hear me?
Yes, ma'am.
Okay, Sarah, so far I was discussing only about type of numbers, which I have actually previously also discussed. You can take a
Yeah.
screenshot quickly if you wish,
Yes,
right?
ma'am. Done, ma'am.
Okay, so this is nothing like I discussed what are natural numbers. So 1, 2, 3, that means counting numbers. Understood? That I told you
Yes,
before.
ma'am.
Anyway, in exam, they'll not ask you what are natural numbers, what are whole numbers, but the understanding of these is very important. Whole numbers, they start from 0. Then integers means if you also include the negative, then it becomes integers, right? Then rational number are the number which is of the form p by q. For example, 2 by 3, I have 5 by 7. All these are rational numbers. But if I have only number, let's say 6, so can I call it rational? Yes, because I can write it as 6 by 1, isn't it? So that means all the integers, they are also rational numbers, isn't it? Right. Then irrational numbers, which are not rational, I mean, not of the form p by q, they are irrational. Understood? So basically, I was saying, Sarah, just quickly, irrational numbers are basically whenever you have fractional power of numbers under root 2, right? So we write it as 2 to the power half. So here you can see the power is fraction, so it is irrational, right?
Yes, ma'am.
Yeah, but all the numbers are not irrational. If I have under root 4, so under root 4, I can write as 4 to the power half. So by this definition, I should call it irrational. But no, because I can write it as 2 square and then power half. So it becomes 2 into 2 and that becomes 2 only. So whenever you have a perfect square inside square root, that is not irrational. Otherwise, 2 to the power 2 by 3 will also be irrational. 2 to the power 1 by 4 will also be irrational. But you have to deal only with these kind of numbers in your syllabus. Okay, next we come to real numbers. So that means rational plus irrational. So if I just quickly draw, let's say a tree type of diagram. Martin, I can't hear you now.
I'm here.
Okay. So I have two types of numbers, rational as well as irrational. Understood? I have given you definitions now. So the rational a number, they also include integers. Integers, right? Or I think I should go anyway. Okay, it includes integers, right? Now, integers are of two types. They are positive integers also. And you can have negative integers also, isn't it? So they both are included in the integers. Now, positive integers can again, they include whole number. Positive integers, right? And then whole numbers will include natural numbers. Is that clear, all of you?
Yes, ma'am.
Yes, ma'am.
Okay. So that was the first topic of this chapter, types of numbers. Now, second topic of this chapter is you should know what are co-primes, right? This is an important term. You will use it in proofs also. What are co-primes? Okay. So the co-primes, any two numbers are co-primes if, you know, Hcf of these two numbers, any two numbers, let's say a and b. So if Hcf of a and b is equal to 1, then they are co-primes. What does it mean? That they have no common factor apart from 1. Hcf is what? Highest common factor. I mean, there's nothing common between them. See, 1 is always common between any number, isn't it? Because, for example, yeah, for example, I take a number 7 and I take a number 5, right? So 7 can be written as 7 into 1. 5 can also be written as 5 into 1. So you can see 1 is always common, like 1 will occur in every number. So the highest factor is only 1, nothing else. So 7 and 5 is one example of co-primes. 2 and 3, right? Another pair of co-primes. Understood?
Yes, ma'am.
Yeah. What else? Can you give me one example, Sarah? Another example.
8 and 6.
No, Sarah. See, 8 can be written as 2 into 2 into 2, right? 6 can be written as 2 into 3. So 2 is a common factor, isn't it?
Oh, come on, ma'am.
Okay, start from a small number. Let's say 2, right? Okay,
Yeah.
3 I have already given you. Think of something else.
5.
Exactly, right? Both are prime numbers. 2 is 2 into 1 only, right? 5 is 5 into 1 only. So there's no factor apart from 1. So 2 and 5 is one pair of co-primes. Understood? There's
Yes,
nothing
ma'am.
common between them. All right. Okay. So understood, Arshia?
Yes, ma'am.
Okay. Now the next topic, see, Euclid's division lemma is not in your syllabus, so I'm not discussing it. Okay.
Okay, ma'am.
And it's nothing else. Basically, Euclid's division lemma is this thing only, as you have learned that dividend is equal to divisor into quotient plus remainder. All right. So this Euclid's division lemma basically say that if you have two numbers, let's say a and b, where a is a greater number, right? So this greater number can be written as b into something which is quotient, and plus you get some remainder. That's it. That's Euclid's division lemma, right?
Yes, ma'am.
Okay. Then there is an algorithm also. Basically, it helps you to find the HCF of two numbers. So algorithm means a series of steps. So Euclid has given some series of steps. With the help of those steps, you can find the HCF of any two numbers. All right. So, but I'm skipping it. It's not in your syllabus. The theorem which is in your syllabus is called fundamental theorem of arithmetic. See, the statement of the theorem is not important. I mean, they'll not ask you to write the fundamental theorem of arithmetic. All right, Arshia. But you should know what does it say. Okay.
Okay, ma'am.
Yeah. So you have to understand like what is the theorem. You don't have to learn the statement or something. Now, theorem is that any composite number. Now, what are composite numbers?
Mm.
Okay. First of all, the numbers which are not co-primes, right?
Yeah.
So which are not co-prime means they have something common in that in them. For example, okay, now try to understand the difference here. One, we have prime numbers, right? And
Yes.
then we have composite numbers. So they are basically like, you can say the numbers which are not prime, they are all composite. Understood? Fine, Martin. So prime numbers mean they are numbers of this type. The smallest one is 2, right? Okay, 3, 5, they are all prime. Why? Because it can be written as 2 into 1. That means how many factors? Only 2 factors. Understood?
Yes, ma'am.
And 3 into 1, so only 2 factors. Then 5 into 1, only 2 factors. So the definition of prime number is that it has 2 factors. Okay. These are important things. They'll help you always. So please note them properly in your copy. Okay. Now, composite numbers, I mean the numbers which are not prime, all the numbers are composite. So how many factors they will have?
3 to 4.
I mean more than 2, right?
Yeah.
More than 2, 3 factors, 4 factors, any number of common factors they can have. For example, 6, okay? It's not a prime number, but so it can be written as product of primes like 2 into 3 into 1. So you can see it has more than 2 factors. Fine, Arshia?
Okay, ma'am.
Okay. So you can take a bigger number, for example, 80. So obviously you can break this into factors. So the fundamental theorem of arithmetic says that any composite number, right? It can be written first of all as product of primes, right? For example, I have 80. So let us do prime factorization of 80. So that means 2 into 4, right? Then 2 into 20, then 2 into 10, then 2 into 5, and then 5 into 1. So you can say that I have written 80 like 2 into 2 into 2 into 2 into 5, right? So first of all, it says that any composite number can be written as a product of prime. Let me take a smaller number. Let's say I have 12, right? So 12 can be written as 2 into 6, 2 into 3, 3 into 1. So 12 can be written as 2 into 2 into 3. Understood? Okay. Second, it says that this prime factorization is unique. Unique means 12 will always have only these three factors, right? So whenever you want to prime factorize 12, you'll always get one, like 2 times 2 and 1 3. Okay. You will not get something else. I mean, you can never get 4 into something. No. You cannot get 5 into something. No. Like this. You will always get 2 into 2 into 3. I mean, this is the unique prime factorization of 12. Understood? There is no other answer. All right. Okay. And then it is irrespective of order. Irrespective of order means like 12. It can be written as 2 into 2 into 3, right? It can also be written as 2 into 3 into 2. Does it matter? No. It can be written as 3 into 2 into 2. So you can start anywhere. Understood?
Yes, ma'am.
Yes. So that means when you are doing prime factorization of 12, so it's not necessary that you start from 2. You can directly start from 3. 3 into 4, and then you can 2 and like this. Okay, Arshia?
Yes, ma'am.
So these are the three things which tell the fundamental theorem of arithmetic tells you that first of all, any number can be broken down into product of primes, and it is a unique representation, and the order is not important. So let us see what kind of questions can be asked from this.
Ma'am, 1 minute.
Okay.
Done.
Okay, done, all of you?
Yeah, I'm doing, ma'am.
Okay. Okay, shall I proceed? Yeah. Right, so this was the difference between composite. So you can write like more than 2 factors here. Okay. So prime factorization, sorry, prime numbers have only 2 factors. Composite number have more than 2 factor. Okay, what about 1? Is it a prime number? Arshia, is it a prime number?
Yeah, no, ma'am.
Why no? Yeah, give me reason. Sarah, is it a prime number?
Yes, ma'am.
Who is speaking? Abdullah?
Yes, ma'am.
Oh, welcome to class, Abdullah. When did you join? Like, did you hear what I was saying?
Yes, ma'am.
Okay, okay. See, 1 is not a prime number. Please note, it is not obeying this definition. 2 factors, I have told you. 1 is 1, right? It can be written as 1. It cannot be written as 1 into something, right?
Yes,
Yes,
ma'am.
ma'am.
So not a prime. It is important. 1 is not a prime number. The smallest prime number is 2. All right.
Yes, ma'am.
Okay.
Yes, ma'am.
So Abdullah, have you understood fundamental theorem of arithmetic?
Yes, ma'am.
Okay. Now see the type of questions that will be asked. First of all, let us see about on this topic, like any composite number can be broken down into product of primes. So you can have questions of this type that find the prime factors of direct question of, right? Okay. This will be like first type of question. So I give you one example. Let's take a small number, 180, let me take. Okay. So you have to prime factorize it. All of you know how to do it, right?
Yes, ma'am.
So I have 180. I can see it is an even number. So better start with 2, or I can start with 5, because any number ending with 0 is also like 5 is one of the.
Ma'am, 2.
Okay. So start with 2. So it is 2 into 9, 18, and then 90. Then 2 into 4 is 8, and then it becomes 10. So 2 into 5 is 10, right? Now you can go with 5. So 5 into 9 is 45. Then 3 into 3, 3 into 1. Okay. So that means 180, this composite number 180, we have broken it into product of primes, that is 2 into 2 into 5 into 3 into 3. That okay?
Yes, ma'am.
Right. Okay, now all of you will do it quickly. 3, 8, 2, 5. Do prime factorization and tell me the answer. So you can start with 5 because you can see a 5 in the end, right?
Yes, ma'am.
Just tell me who is having problem.
Completed.
Okay, good. Yes, what is the answer?
It's 3 square
Okay,
into 5 square into 17.
okay. Is everybody getting it?
Yeah, ma'am.
Ma'am, just 1 minute.
5 square plus 3 square plus
No,
7.
no, it's not plus, Martin. It's all
Oh,
multiplied, right?
into.
Product of primes.
Ma'am, yes, ma'am, I got it.
Yeah, okay. So just 2 I'm giving in the homework. You will do 5005, right? And the next is 7429. So this you will complete. So this can be first type of questions which can be asked, right? Now let us see second type of question based on fundamental theorem of arithmetic. You can have questions of this type which will be based on uniqueness of fundamental theorem of arithmetic. I'm writing in short, you can complete it. Okay, example. Prove that there is no natural number n for which 4 to the power n, right, ends with digit 0. proof. So you have to show that there is no n for which 4 to the power n ends with digit 0. Like whatever value of n you take, 4 to the power 1, 4 to the power 2, 4 to the power 3. So the answer will never end with 0. That you have to prove. Understood?
Yes, ma'am.
Yes, ma'am.
Right. Okay. For example, 4 to the power will give you 4. 4 to the power 2 is 16, right? 4 into the power 3 is 16 into 4 something. So you'll get 64 and like that. So you can see there is no 0 in the end. So you have to prove this thing. Got it? Right. So here we will use uniqueness of fundamental theorem of arithmetic. How? Like for any number, you have to write this, that for any number to end with 0, right? It should be divisible by 5. Right? Or we can say 5 is one of the factor. Is this understood? Like if there is any number which is divisible by 0, so we know this thing. For example, I take a number 20. So I know that 20 will be divisible by 5 because it is having a 0 in the end, isn't it? And that you can check also. I mean,
Yeah.
you do prime factorization of 20. So 2 into 10, 2 into 5. So you can see 5 is always one of the factor. Any other number you can pick, right? 30. So 2 into 15, then 3 into 5, and then 5 into 1. So you can see, and again 5. So 5 is always there. Like it's always one of the factor, isn't it?
Yes, ma'am.
Okay. Okay. But if I write like 4 to the power n, right? So 4 can be prime factorized at 2 into 2 to the power n. That's the only prime factorization.
Yes, ma'am.
Yes. So, or I can write it like this, 2 to the power 2 into n, or you can write it 2 to the power 2n. Okay. Right. So you can see there's no 5 here, right?
Yes, ma'am.
So, I mean, these terms are not even important. Look at this only. So you can see there is no factor of 5 here. So we will write all these things, that the only prime in the factorization of 4 to the power n is 2. So 2 is the only prime number, right? Okay. So by the uniqueness of fundamental theorem of arithmetic, okay, we know that this prime factorization is unique. I mean, it will always be 2 into 2. There can never be any other number. So there is no chance that sometime we get a 5. All right.
Yes,
Okay.
ma'am.
That's the theorem. So it is saying that 4 is always 2 into 2, or 4 to the power n is always 2 into 2 to the power n. So there is no chance that somehow there is a 5, or sometime there is a 5 will occur. No. So there we will write that there is no other prime. There is no other prime. So this we actually saying by the uniqueness of fundamental theorem of arithmetic. All right. So it will always be 2 into 2. 5, there's no chance of a 5 here. So that means 5 does not occur in the prime factorization of 4 to the power n, right? So
Ma'am,
yes,
actually, there was fire in our building, so they told us to get down.
fire. Okay, sure. I'll ask the office to give you recording later.
Yes, ma'am. Thank you.
Okay. Take care, please. Okay, other students. So 5 will never occur. So we will say that 4 to the power n does not end with 0 for any natural number n. Is that clear, all of you?
Yes.
Yes, ma'am.
See, this is a simple concept, but you have to explain it. And one of the question is also given in the NCERT. There is 6 to the power n. So that I'm leaving for you as a homework. So here, the homework part is this. Check whether 6 to the power n, right, can end with digit 0. For any n, for any, not any natural number n, right, counting number. Because I don't want negative n, it's only positive, natural number. So that's the homework. Same way you have to write, okay? So hint is that 6 can be broken down as 2 into 3, right? 6 to the power n is 2 into 3 to the power n. So again, you can see there is no 5 here, okay? Then you have to write the same lines and then you can conclude that 6 to the power n does not end with 0 for any natural number n. So 3 type of questions we have discussed so far. Has everyone written?
Yes, ma'am.
Okay. Abdullah.
Yes, ma'am.
Okay. Okay, next type you can see here is this type of question. Or the topic is Hcf and Lcm by prime factorization. Right? So this is the 4th topic in this chapter. So Hcf can be found by Euclid's division algorithm also, right? But that method we don't have to do. We have to find Hcf by prime factorization. Like how do we do it? First of all, what is Hcf? Hcf is highest common factor that you all know, right? Highest common factor, that is called Hcf. So when we take two numbers, right, and we do the prime factorization, so the Hcf is found like this: product of smallest power. I'll give you example, please note down. Product of smallest power of each common factor, right? And LCM. LCM, the full form is least common multiple. Now, when after doing prime factorization, this can be found like as product of greatest power of each prime factor. Please note it down, then I'll explain with the help of an example. Okay, written. Now, please note one thing, please underline. Here you have to take smallest power and here you have to take greatest power. Please underline this thing. Right? Okay. Now, second thing, please note, here you have to take only common factors. Please make it a box on it. Only the common factors you have to take. And here you have to take each factor, whether it is common or not common. Let's take one example. Find the HCF and LCM of question, right question. Find the HCF and LCM of 90 and 144 by the prime factorization method. Right?
Yeah.
Okay. So how do we do it? First of all, do prime factorization of 90. So I can start with 3, right? 3 into 3 and then 0. Then 3 into 1 and 0. Then 2 into 5, 5 into 1, right? So 90 can be written as 3 into 3 into 2 into 5, okay? Which I can write as 3 to the power 2 into 2 to the power 1 into 5 to the power 1. Is that clear? Now
Yes.
144. So 144, 2 into 7 and then 2. Okay, then 2 into 3 is 6 and then 12, so 6. So 2 into 1 and 8, 2 into 9, 3 into 3, 3 into 1. So 144 is 2 into 2 into 2 into 2 into 3 into 3, which I can write as 2 to the power 4 into 3 to the power 2. Is this clear, all of you?
Yes, ma'am.
Okay. Now what about HCF? So HCF of 90 and 144. So when you are finding HCF, you have to take the smallest power, right, of each common factor. So how many common factors are there? I can see 2 is common, right? 2 is there in both, but I'll take the smallest power. That means 2 to the power 1. Understood? Then 3 is there in both the numbers and both have 3 to the power 2. So I'll take 3 to the power 2. So this will become 2 into 9, 18. So HCF is 18. Right? Now let us take LCM of 90 and 144. So look at the definition here. The product of greatest power of each prime factor. So I'll take all the prime factors like 2 into 3 into 5. Now what about power? So here 2 to the power 1 and 4. So I'll take the greatest power, 2 to the power 4. Okay. 3 to the power 2, same. And then 5 to the power 1. So you don't have to skip this 5 to the power 1. You have to take each prime factor. Because in the second one, I can write 5 to the power 0. Does it matter? Right? If I can write 5 to the power 0 here, because anything to the
Yeah.
power 0 is 1. So which is the greatest power? It is 1. So I'll include this 5 to the power 1 here. Or you can mention this thing, no problem. It will help you. So you can compare which one is having greater power of 5. So LCM will become now 2 to the power 4. That means 4 into 4 is 16 into 9 into 5. So you please multiply this thing. So it is 16 into 9 into 5 is 45. Quickly multiply, tell me how much is it? It will be 720, right? You people are very slow in calculation. Anyway, one question I'm giving for your practice here, homework you can say. Find HCF and LCM of, write down, find HCF and LCM of. This time I'm giving 3 numbers, 40, 36, 126. So same way you will prime factorize and then you will look at the powers.
And could you go back?
Yeah, sure. Yes, Abdullah, is everything understood? Abdullah, please unmute your mic.
Yes, ma'am.
Okay, is everything clear so far?
Yes, ma'am.
Please ask questions if you want to ask something, okay?
Okay, ma'am.
Please note homework and all of you have to complete all these questions which I'm giving. It will help you to practice. Now next, okay? The fifth important thing in this chapter is this formula. The questions will be asked from this, that for any two numbers, A and B, A and B, right? The HCF of these two numbers multiplied by LCM of these two numbers is actually equal to product of these two numbers.
Okay, ma'am.
Okay. I should not write numbers, I should write integers. Yeah, because it is applicable for integers, like not irrational numbers. Right, now the first type of question which will be asked is like that. Find the LCM and HCF of the following pair of integers and verify LCM into HCF is equal to product of integers. So you can have number like 336 and 54, let's say, right? First example. So you have to find the LCM and HCF first of all. So can you find, like, do prime factorization quickly? So 336, 2 into 1, and then 13, so 2 into 6 and 8. Now 2 into 8 and 4, 4, 2, 2 into 2, 3 into 7, and 7 into 1. Please all of you check if I'm wrong. 2 into 2 is 4, it becomes 14. So 2 into 7 is 14. Then 3 into 9, yeah, 3 into 3, 3 into 1. So 336 can be written as 2 to the power 4, right? Into 3 to the power 1 into 7 to the power 1. Then 54 can be written as 2 to the power 1 into 3 to the power 3, right? So I want HCF. So I'll take the smallest power of common factors. So 2 is a common factor, smallest power is 1. Again, 3 is a common factor, smallest power is 1. So the HCF is 2 into 3, 6. Now LCM. All the factors you have to take and greatest power. So 2 to the power 4, then 3 to the power 3, and 7 to the power 1. So it becomes again 8 into 4, 16 into 9 into 7. So that you have to multiply. Please tell me how much is it? Please do it here. 16 into 9, right? 6 into 9 is 54. Carry 5, 9, 14. So it is 144 into 7, 28, 2, 30, 7.
1008.
Yes. So it is okay. You are back, Sarah. 1008.
Yes.
Right. So you have to. So we have found HCF and LCM. Now you have to verify. That verify the LCM into HCF is equal to product of integers, right? So first of all, multiply HCF into LCM. So I have HCF multiplied by LCM is how much? So it will be 6 multiplied by 1008, which is equal to 6 into 8 is 48, then 4, 6 in 6048, right? And then product of integers. So one integer is 336, another integer is 54. Now please check what are you getting quickly.
Excuse me, ma'am.
1.
Yes, sir, sure.
Can I go bring my charger?
Sure. Okay.
Ma'am, 18144.
No, I think you should get the same number, isn't it? Check again.
Yes, ma'am, I'm getting this only.
Same, yeah? 6048.
Yeah.
Okay.
No. Ma'am, I'm
No.
getting 18144.
Okay, let me just check with the help of my calculator quickly. 336 multiplied by 54. Oh yes, I'm getting different. So I'm getting 18144,
Yes, ma'am.
right? So anyway, you can write that in this case, it's not verified. How will you conclude? That here, no, but this way the theorem will not be valid. Is there any mistake I have done? Is my LCM correct?
1 minute.
Yes, Martin. See, this is right, 18144.
Really?
Is this
Correct.
prime factorization correct or there's some mistake here? Let me just check again. 336. 2 into 1 is 2, 13. 2 into 6. Two to the power 4. Yeah, this is fine. Now 54 is that is also right. So HCF will be, yeah, 2 to the power 1 into 3 to the power 1, that is 6, fine. And LCM will be 2 to the power 4 into 3 into 7 to the power 1. Oh, there's a mistake here. 3 to the power 3, right? It's not equal to 9. It's equal to 27, right?
Yes, ma'am.
Oh,
I took the square into 27 and then into 7. 2 to the power 4 means, right? 2 into 2, 4. 4 into 2, 16. And no. 2 into 2, 4. 4 into 2, 8. 8 into 2 is 16. That is right. What mistake I'm doing here? Just check. Okay, I can do one thing. You can just check this particular question later on. I can give you one more example, right? Right. Please
Yes,
just
ma'am.
check it once again instead of wasting time. Let me take another example. For example, I take number 90 and 144, right? Now you do prime factorization. So 90 is 2 into 4 and then 10, 45. 2 into, sorry, not 2, 5 into 9, 3 into 3, 3 into 1. Okay. And 144 is 2 into 7 and 2, 6, 2 into 1 and 8, 2 into 9, 3 into 3, 3 into 1. So 90 can be written as 2 to the power 1 into 5 to the power 1 into 3 to the power 2, right? Now 144 is written as 2 to the power 4 into 3 to the power 2, right? Now what are the common numbers you can see? I can see 2 and 3. So the HCF is 2 to the power 1 into 3 to the power 2, clear?
Yes, ma'am.
So
Yes.
that is equal to 2 into 9, which is equal to 18. And LCM is the highest power, that means 2 to the power 4, 3 to the power 2 into 5 to the power 1. So again, this is 16 into 9 into 5. So the same example I have taken, which we have done before. So that is how much? I think we did it here, 720, right? Now we do the verification. So you check HCF multiply by LCM, right? How much is it? It is 18 multiplied by 720. Okay, and then you multiply these two numbers, these two. 90 into 144. So whatever you get here, so they both will be same. So that will be verified. Okay. Please complete the calculation part. So in the next class, I'll be discussing about irrational numbers. I hope this much part is clear to you now. Irrational number is actually important from your for your examination point of view, right?
Yes,
Because
ma'am.
all these things you have studied in your previous classes also, Hcf, Lcm, and etc. Definitely you are going to get question from irrational numbers. Okay.
Ma'am, can you show the previous one? Previous, can I take a screenshot?
Yeah, please check some calculation mistake is there. Okay, Martin. Please do prime factorization and then verify it.
Okay.
All right, Arshia. Okay, I have my next class now, so you people can leave.
Thank you, ma'am.
Okay, bye.
Ma'am, can you go back? Is there anything other than this?
No, actually we were stuck in the calculation part when you were not here.
Okay, ma'am. Thank you, ma'am.
Okay, bye. Hello, Harsha, Hamna.
Yes, ma'am.
Okay. So Harsha, you were not there in the class.
Yes, ma'am.
Okay, so we did some questions from 13.2 in that class and few questions are remaining. So I think let us complete that. Okay. Hamna, how many questions we did? Up to 4th, I think we have done.